Once we have determined the correlation coefficient between two quantitative variables, we are ready to move on to the next step, which is determining the equation of the regression line, also known as the data's line of best fit. The purpose of this line is first to see the trend, and second to make predictions based on the data if and only if the correlation coefficient is significant. If you recall in the previous videos on correlation, we're trying to see if there's a relationship between the number of classes missed and the final grade. Once we had built the scatter plot, I had drawn an approximate line that shows the trend. What I didn't mention at the time is that I tried to draw the line that went as closely as possible to all of the points on the scatter plot, hence the name, the line of best fit. To be more specific, the line of best fit is the line where the sum of squares of the errors in the y direction from each point to the line is at a minimum. Okay, take a look at this scatter plot. There indeed seems to have a positive trend. First, I'll remind you that the points are the reality, the observed values. On the other hand, the line of best fit is a tool for prediction, so the error will be from each point to the line. Let's take a look at the first point. See how it's not directly on the line? So this gives us the first error. Our second point isn't directly on the line either, so there's error 2. Same for the third and fourth points. Fifth point, though, is directly on the line, so here the error would be 0. Points 6 and 7 are quite far and also have their respective errors. Now the line of best fit is the line out of all the possible lines you could draw where the sum of the square of these errors is the smallest. The reason we need that line is that the values of y, the dependent variable, will be predicted based on the values of x, the independent variable. So the closer overall the points to the line, the better the prediction will be. Now that's all fine and dandy, but how do we determine that line? Of course, it makes no sense to go and draw oodles of lines and then calculate the sum of squares for the errors for all of them and then choose the lowest one. It's actually rather simple because we can use the equation for a straight line we've seen back in high school. Remember this equation where you have given values of x and y's? You have m, which is the slope of the line of best fit, and b, the intercept. As a reminder, the slope is how pronounced the dip in the line is. For example, in this case, the yellow line's slope is more pronounced than the green line. A slope can be positive, going up like this, or negative, going down like this. As for intercept, that simply indicates where, on the y-axis, does your line of best fit actually cross. Bringing back the absence versus final grade example, if we continue our line of best fit towards the y-axis, it gives us a value just over 100. There are a few ways to calculate the intercept and the slope. The method we've seen in high school would yield imprecise results, so we will use these two formulas. Again, they might seem intimidating, but take a close look and you'll see these are all values we've calculated already when finding the correlation coefficient, so I won't go over them. If you need a refresher, feel free to watch the correlation 2 videos. But let us move on and find the actual m and b values. Starting with b, the intercept, here's the table we calculated in the correlation video for our example. Again, if you need a refresher, watch the correlation 2 video. So I'll go very quickly and simply plug in the numbers, like so. And now we're ready to do the math. So first we do all the multiplications, which gives us this. Then we simply do the subtractions for these results. And finally, this last division gives us our intercept. Now we can move on to the slope, which is this equation. Again, here are the values we calculated previously, so we'll go on quickly to replacing the values equation, which gives us this. We can move to the actual calculations now. So again, we do the multiplications for these results and then the subtractions, which gives us a slope of minus 3.622. A cue to see if you're going in the right direction. Remember the scatter plot we drew in the beginning. The line was actually pointing downwards, so it's good that we have a negative slope. We now have all of the elements we need to fill out the line of best fits equation, which becomes y is equal to minus 3.622x plus 102.493. This means we're ready to start doing some predictions. For example, what grade, the y value, would a student get if she missed 10 classes, x value? All we have to do is plug the numbers in the equation and solve for y, which would give us 66. Note that the end result is rounded to the same degree than the original data. Now you must be cautious, of course, with such predictions because they are made based on present conditions. What if in the following week the prof changes the class format to only assigning chapters to read in the book and there's no need to go to class? And they also do not take into account all of the factors that can influence the dependent variable. What if the student that misses 6 classes actually works and studies harder than the student that missed 3? So don't throw all caution to the wind and be critical of the results of your predictions. When dealing with regression, you may encounter r squared. This is called the coefficient of determination, and it is the measure of the percentage of variation of y that is explained by the regression line and the independent variable. As you've seen, most of the points in our scatter plot are not directly on the line of best fit. There's deviation on the y-axis of where our points are placed versus the line. Now, to really understand deviation, we need first to draw a line that represents the mean of our y value. Now, I'll zoom in on this bit so we can see better. Voila. It's easy to see that there's a gap between the point and the line of best fit. Now, that's called the total deviation. We can divide that deviation in 2 parts. The explained deviation, which is the distance between the mean of y and our line of best fit at our given point's y coordinate, and the unexplained deviation, which is the vertical distance between our actual point's y and the line of best fit. Now, mathematically, our coefficient of determination is the ratio of the explained variation to the total variation. We won't go into details into how to calculate these variations because the simplest way to calculate the coefficient is simply to take our correlation coefficient r and square it. So in our classes missed versus final grade example, we had a correlation coefficient of minus 0.944. So minus 0.944 squared is 0.891. This means that 89.1% of the variation in grades obtained is explained by the variation in the number of classes missed. This also means that 10.9% of the variation is explained by something else. By what, though? Is it the amount of time studied? Is it simple intelligence? Now that's for the researchers and for us eventually to find out.